Okay, ladies and gentlemen, you are welcome. Please, if this is the first time you are coming to my YouTube, please subscribe and join the YouTube community so that you can have access to our videos. And don't forget to turn on your notification so that always you can have our videos when we upload. Introductions to alkenes. Alkenes are hydrocarbons that contain at least one double bond. So in the case of alkenes, there are hydrocarbons that at least in them they have one double bond. So they must have at least one double bond. And they are unsaturated compound. So because they are unsaturated, it means that they have fewer hydrogen atoms than alkenes. So usually, especially in the case of alkenes, they are deficient in 2 hydrogen atoms when you compare it with alkane. Alkenes are important in organic chemistry due to their reactivity and use in manufacturing. So these alkenes, they are very, very important in organic chemistry because they are very reactive and they are used in manufacturing a lot of industrial products in the industry. So as we can see, ladies and gentlemen, this is examples of alkenes where we have ethylene, propylene, and we have butylene, butadiene, and hexatriene. So as you can see, at least in alkenes there must be at least one double bond. So as you can see, we have double bond here. We have another double bond here in propylene. We also have double bond here in butylene, and then we have 3 hydrogen bond in hexatriene. And then also at the same times in butadiene we have 2 hydrogen bonds. So generally, ladies and gentlemen, in alkenes there must at least one carbon to carbon double bond, and the number of hydrogens is fewer in the case of alkenes compared to the corresponding alkenes. So now, what are the general formula for alkenes? The general formula for alkenes, as we can see, is CnH2n. And how do we get the value for alkenes? So if you can see clearly here, alkenes has a general formula of C2H2n plus 2. So if we have n, let's say here we have n is equal to 4. So how are we going to do it? So we have to take the formula which says we have C2H, we have Cn, we have the formula is, let me erase it. So the formula is, as we can see, is CnH2n. So this is the formula, CnH2n. So with this formula, how do we do it? When n is equal to 4, we can easily substitute. So therefore, we have C4, we have H2 times 4, and this will give us C4H8. So this is butene. So this is the general formula where n is the number of carbon atoms. And as we can see from here, ladies and gentlemen, in the case of alkenes, the formula, this is of course butane, and this is the corresponding alkene, which is butane. So you can see between alkene and alkane, the difference is that there are deficiency of 2 hydrogen atoms in butene. So that is to tell you that the number of hydrogen atoms in alkane or in alkene is fewer than the number of hydrogen atoms that are found in the corresponding alkane. So that is actually the formula. So with this formula, you can use it to get ethene, propene, butene, pentene, hexene. All the names will be ending with ene. So this formula indicates that alkenes have twice as many hydrogen atoms as carbon atoms minus the number of the double bond. So as you can see, it has twice, or it indicates that alkenes has twice as many hydrogen atoms as carbon atoms minus the number of double bonds. So as we can see, the number of hydrogen bonding in alkenes is twice less than the number of hydrogen atoms that are found in the corresponding alkene. And then the simplest alkene is ethene, which is also known as ethylene, with the formula of C2H2N. Sorry, C2H4. So now, what are the structure of alkenes? Alkenes have a planar or flat structure around a double bond due to sp3 hybridization. And the carbon-to-carbon double bond consists of one sigma bond and one pi bond. So in the case of double bonds that are present in the alkenes, like let's see here, 18, we have carbon-to-carbon double bond. So in this double bond, one of these double bond is sigma bond, and the other one is pi bond. So therefore, in the double bond, we have one as sigma bond and we have one as pi bond. And these pi bonds are formed as a result of side-to-side overlap of p orbitals, and the pi bond is more reactive than the sigma bond. So the pi bond is formed as a result. The pi bond is formed as a result of side-to-side overlap. So the bond in pi bond is more reactive than that of the sigma bond, and this is how the pi bond is formed. As you can see, this is a p orbital, and we have two p orbitals here. So this is a p orbital and this is another p orbital. So as you can see, these orbitals collide side to side, which result in the formation of pi bonding molecular orbitals. So it is formed as a collateral or side-to-side overlap between p orbitals to generate a pi bonding molecular orbital. And the bond is very strong and it is more reactive than the sigma bond. And of course, for the sigma bond are formed as a result of head-to-head overlap. So when you have two sigma bonds, they will collide head-to-head, and as a result of that, you are going to have a sigma bond. So assuming now you have a compound, let's say you have something like this. Let's say you have C3H8, and of course this one, it appears like this. So we have H3 here, and we have H2, and here we have a double bond. So if you now ask, what are the number of sigma bonds that are in this compound, in this structure here? So as we can see, this is okay, here there is one hydrogen atom, and this one is going to be C3H6, and this is propene. So as we can see here, if you ask to calculate the number of sigma bond and pi bonds that are here, so the best thing to do is count the number of atoms. So if you look at it, we have 3 here, we have 6, and this will give us 6 plus 3, this will give us 9. So 9 minus 1 will give us 8. So whenever you want to calculate or you want to know the number of sigma bond, you take the atoms, you add all the atoms together and you minus it by 1, and that will give you the number of sigma bond. So here we have 8 sigma bond and we have 1 pi bond. Remember, when we have double bond, one is sigma bond and one is pi bond. So we have 8 sigma bond and we have 1 pi bond. So this is how to calculate the number of sigma bond and pi bond. So the next thing that we are going to look at, ladies and gentlemen, is the physical properties of alkenes. Alkenes are usually colorless and have a gaseous or liquid state at room temperature. So they are usually colorless, and some of them, especially the first members, they are gaseous, and also there are liquids. There are some of them that are liquids at room temperature, and they have lower boiling point compared to corresponding alkanes due to weaker intermolecular forces. So the number of hydrogen bonds, you may be given a series of compounds and you will be asked to arrange them based on their boiling point. So you look at them. The alkenes or the corresponding alkanes have higher boiling point than the alkenes. So alkenes have lower boiling point due to their weaker intermolecular forces. So the next thing is, of course, as alkenes are insoluble in water but soluble in organic solvent like benzene and ethanol. So these are the typical examples of non-polar solvent that dissolve alkene. So it is insoluble in water generally. And as we can see from here, we have the compound. So as we can see from ethene, as you move down, the boiling point is increasing. So as you move down from ethene to 1-octene, the melting point is increasing. And of course, the boiling point is also increasing as you move down the family. So as you can see, the boiling point increases with an increase in the number of carbon. So then reactions of alkenes. Alkenes readily undergo additional reactions. So the major types of reaction that is specific to alkenes is additional reaction. And such additional reaction, it can be halogenation, that is addition of halogen, hydrohalogenation, that is addition of alkyl halides, and then haloalkanes, and then hydration. And the reaction, this additional reaction is a reaction that involves, because as you are adding an atoms or group of atoms, so it means that at the same time you are breaking pi bond. And as you are breaking down one pi bond, then you are creating two new single bonds. So you are breaking pi bond and you are making new single bond. That is what happens in additional reaction. And the reactivity of alkenes makes them useful intermediate in chemical reaction. So as we can see, basically these are the major types of reactions in alkenes. We have substitution reactions, we have polymerization reaction, addition reaction, and oxidation reaction. These are the major types of reactions of alkenes. If you need to understand the details of the reactions of alkenes, you can check the description box of this video and then you can click on it. You will have a wide knowledge of the reactions of alkenes. So I have a complete video on that. You can click on the link on the description box of this video so that you can watch it. Then the next thing is, of course, the nomenclature of alkenes and their basic rules. So the first thing, when you are going to name alkenes, the longest carbon chain containing the double bond is selected as the parent chain. So when you are given a compound, so the first thing is to select the longest carbon chain, which will be considered as a parent chain. So in the case of alkenes, we usually select the longest carbon chain that contains a double bond. And then the double bond is assigned the lowest possible number in the chain. So you always start numbering from, like for example, let me just give example. If you have something like this, so you see this is a compound here, and as you can see from the compound here, how do you number this and how do you consider the longest carbon chain? So you cannot take this from here going to say 1 2 3 4 5 or 1 2 3 4 5 6. So already here is 6. So you take the longest carbon chain that is pairing the double one. Let's say here is another one, it's 6. 1 2 3 4 5 6. So you are not taking this because we are not considering the double one. So you have to take the one that is pairing the double bond, even if this one is 5. So after you do that, the next thing is to assign a number. From which direction are you supposed to number this compound? Is it from this direction or from this? No, the answer is you name it from this 1, 2, 3, 4, 5, 6. So therefore, if you look at it, this is where you are going to get the lowest possible number that is bearing the double bond. But if you do it from here, 1, 2, 3, 4, so you see it is 4 here. So if you take this one, it's wrong. So you always take it from the direction where you will assign a number to double bond with the lowest number. And of course, the suffix ene is added to the root name to indicate the presence of a double bond. So if it is alkene, it is going to be alkene. Like for example, this one is 1, 2, 3, 4, 5, 6. So it is 6. So it is going to be 2-hexene. 2-hexene, meaning that there are double bond at carbon 2. So this is actually a typical example, as we can see, ladies and gentlemen. Let me delete this so that it will be much more clearer. So if you can look at this one, ladies and gentlemen, why is it that while naming the compound, you see that it started from which direction? As you can see, it started from here as 1, 2. So why not is from here 1, 2, 3? Because the double bond, if you started in this direction, is 3, and if you started from here is 2. So we always take the lowest possible number. So that is why it started here. And at the end, we have 2-pentene, because there are 5 carbon, and then the position of the double bond is indicated with the 2. And then if you look at the other one here, you also started numbering 1, 2, 3. So because the double bond is at carbon 3, and if you start, so you see here, if you start naming 1, 2, 3, from this one to 1, 2, 3. So it is all at, if you started from this direction, the double bond is still at 3. And if you also started from this direction, the double bond is still at 3. So why is it that you are not starting from this direction? It's because of the methyl group. So if you name it from here, the numbering in methyl group will be at position 4. So that indicates that the position of the methyl group will have the higher number compared to while you start numbering from here. So that is why we have 2-methyl-3-hexene. And then of course another one you see here, we have 1, 2, 3, 4. So we started from here. So that is why it is bearing 1. And we have ethyl group at position 3. So this is how to do it. It ended with ene, and you also indicate the position of the double bond by numbering, but you have to take the one with the lowest number. And also in terms of the substituent, you have to also take the one that will give you the lowest number, as in the case of 2-methyl-3-hexene. So then how do we name the alkenes with a multiple double bond? So when the multiple double bonds are present, so their positions are indicated by numbers separated by hyphens. For example, the suffix is going to be diene if it is 2. If it is 3, it's going to be triene, etc. And it's used for compound with 2 or more double bonds. So if you have a compound that have 2 or more double bonds, so you use diene, triene, and you use comma to be in between the numbers, and you use hyphen between the numbers and a letter. So the position of a double bond are listed in the name in increasing order. So let's look at, like for example, in this case, because we have 2 double bond at position 1 and we have it at position 3, so that's why here we have 1,3-hexadiene. 1,3-hexadiene because there are more than one double bond. So then the examples of nomenclature. Here we have 1-butene. So 1-butene, of course, as you can see here, is an alkenes with a double bond starting at carbon 1 in a 4-carbon chain. So if you are to write this, you have something like this: 1, 2, 3, 4. So it means you have double bond at carbon 1. So that is why it is called. So when we said 2-butene, it means that the double bond is at carbon 2. When you have 1,3-triene, it means that you have something like this. You have it at carbon 1, and then you have it at carbon 1, and you have it at carbon 3. So this is 1, this is 2, and this is 3. So we have it at carbon 1, and we have it at carbon. That's why it is 1,3-triene. So it contains 2 double bond at position 1 and 3. So isomerism in alkenes. Alkenes exhibit structural isomerism such as positional and geometric isomers. So in the positional isomer are compounds that have the same molecular formula, the same functional group, but the different position of functional group or a substituent. As we can see here is chlorine. It's at carbon 1 here, and it is at carbon 2. So it is just the change in the position of the substituent or the functional group. And then in the case of geometric isomers, they differ in the spatial arrangement of your groups around the double bond. So usually it's just based on the difference of spatial arrangement of groups around a double bond. As we can see, we have 6. When you have 6, it means that you have 2 groups at the same plane. And then for the trans isomerism, it means that it is transverse. So that is why you see this one is transverse to this, and this one it is in the same plane. So that is in the case of geometric isomerism. It applies to only compounds that have double bond. And also we have EZ nomenclature, which is used to specify the configuration of double bonded carbons. So in summary, alkenes are unsaturated hydrocarbons characterized by at least one double bond, and their nomenclature follows specific rules based on the position and the number of double bonds. So understanding their structural properties and naming is fundamental in organic chemistry. Thank you very much, ladies and gentlemen. Don't forget to subscribe and join to my YouTube community. See you next.